Hello again. This is Math 1120 coming to you from the College of DuPage, and this lecture is the continuation of the one entitled Introduction to Force and Newton's Laws. Again, I encourage you to be an active learner as you watch this video. Okay, so previously and qualitatively, we've learned that when an object is acted on by a non-zero net force, it accelerates. We now want to know the relationship between the acceleration and the force. That is, what Newton's second law is all about. So, experimentally, what we can see is that a constant force causes a constant acceleration. And there are experiments demonstrating the direct proportion between an applied force and the resulting acceleration. If we double the force, we double the acceleration. Again, that demonstrates a direct proportion between the applied force and the resulting acceleration. Similarly, if we half the force, it halves the acceleration. Again, demonstrating that these are directly proportional. Moreover, when we see that the net forces are zero, that means the acceleration has to be zero. That means that something moves at a constant velocity. And that comes from experiments showing that an object's acceleration has the same direction as a net force acting on the object. The net force here is zero, so there is no acceleration. Everything moves at a constant velocity. We also can see that a constant force in the direction of a motion causes a constant acceleration in the same direction as the force. And so you see that there is a constant acceleration. All those vectors are the same length, but what happens is there is an acceleration happening, and that means that these arrows are getting longer. The velocity is increasing, and so the force is increasing. So those experiments show that an object's acceleration has the same direction as the net force acting on the object. Last but not least, here what we have is a constant force opposed or opposite to the direction of the motion, causes a constant acceleration in the same direction as the force. So you see, if you're going this way, the velocity is, you're pushing the other way, you're having an acceleration that's in the opposite direction of the velocity. That causes the velocity to decrease. And so this is an experiment showing that an object's acceleration has the same direction as the net force acting on an object. Okay, so if we put this all together for a given object, the ratio of a magnitude f of a force has a magnitude a of the acceleration is constant. So the ratio of f to a is constant. And this ratio is called the inertial mass, or simply the mass. So what we're saying here is mass is equal to force divided by acceleration. Or an equivalent statement is that you see here I can multiply both sides by a, so that would be F equal ma, or A equals F over m. And so the concept of mass, which we introduced up here, is a familiar one. So if you hit a table tennis ball with a paddle and then hit a basketball with the same force, the basketball has a much smaller acceleration because it has a much greater mass. When a large force is needed to give an object a certain acceleration, the mass is large. When only a small force is needed for the same acceleration, the mass is small. So the greater the mass, the more the object resists being accelerated. Thus, mass is a quantitative measure of inertia. There are numbers associated with it. Really, if you understand this equation, you pretty much understand all of that. So the SI unit of mass is the kilogram, and it's officially defined to be the mass of a chunk of this alloy kept in a vault near Paris, but the kilogram is the unit of mass, as we've talked about before. But now we can actually define what is a Newton, and this is the definition of a Newton, including the units. 1 Newton is the amount of force that gives an acceleration of 1 meter per second squared to an object with a mass of 1 kilogram. That is, a Newton is equal to 1 kilogram meter per second squared. And so here we see some more experimental kind of things. A known net force, you see we sum all the forces, causes an object with a mass m1 to have acceleration a1. If we apply the same force to a second object, what will happen is we'll get the same result. Now when two objects are fastened together, this will be m1 and m2, and so you actually get a different acceleration here because we're adding m1 and m2, that's an a3, and here we get an a1 and a2 that are the summation of the forces, and again there is this relationship that exists, and fundamentally it is F equal ma. That's also known as Newton's second law, which is what's saying here. Now, this is a vector, however, because we've talked about the direction as well. So here's the statement in terms of the vector form. The vector sum, or the resultant of all the forces acting on an object, equals the object's mass times the acceleration. And this is a vector equation. And the acceleration, of course, is the rate of change of its velocity. So the net vector force is the mass times the vector acceleration. And the acceleration has the same direction as the net force, the resultant force. The units are newtons, but that is kilogram meter per second squared. Now, if the vector acceleration equals 0, the net force has to be 0, because you don't have a force unless you have an acceleration. And the forces in this equation are applied to a single object with mass m. Now, this is true for the components as well. So the net force in the x direction is equal to ma in the x direction, and the net force in the y direction is that. So often we can do solving vector problems by components, which is what we've done almost every time in this class. To use these equations, you must first find the components of every force acting on the object, and if any acceleration component is 0, the corresponding sum of the force is also 0. Now, this does assume that the mass is constant, and in our universe that's pretty much true. Some of the things that Einstein studied had the mass changing, but that's the case. And the other thing is that these are also true in only an inertial framework, which again is what we're dealing with almost all the time in this course. Here's an application to biology, and I just mentioned this. This is more of a qualitative example, not a quantitative example. Scientists have found that applying a compressive force, like squeezing them, to cancer cells essentially causes them to revert to normal behavior. Now, this doesn't change the mass of the cell, but it changes the volume, so it squishes them down. And since cancer cells have abnormalities that cause them to divide and grow out of control, that's what you want to stop. Now, squeezing the cells does not remove any of these abnormalities, but it changes the way they behave, curiously, inducing them to form smaller colonies that grow in a normal, orderly fashion. And even after the compressive force is removed, they still behave themselves. So, they don't think that this is going to be a treatment that there is going to be used because you don't want to squish people's body parts and things like that with a lot of pressure, but they hope to be determined that some of these changes that happen can be emulated by drugs, and that'll have similar effects. And I think I've already said this, but like the first law, which says an object remains at motion or at constant velocity unless a force is applied, the second law, F equals ma, is valid only in inertial reference frames. Let's look at a few examples. So here we consider a very simple application of Newton's second law. A worker with spikes on their shoes pulls a horizontal force of magnitude 20 newtons on a box with mass 10 kilograms resting on a flat, frictionless surface on a frozen lake. Now you see it's a very slick lake, that's why they need the spikes, and there is no friction. That's probably not 100% true, but that's what we're saying here. We say, what's the acceleration of the box? Well, and also it often helps to draw a picture, and so this is what the picture is going to look like. So here's your box. The mass is 40 kilograms, and here's the guy. He's pulling on it with a tension of 20 newtons. Note that there is the weight of the object that is actually a force going down. But what happens is that the ice is also pushing up. That's the normal force that we talked about. So those two forces balance one another and aren't in play. But here you have a force of 20 newtons going this way in the x direction. So there's our picture. Well, the net force is equal to m, and the only place that there's any action that will happen is going along the x direction, because this is in balance, these two. So let's see, we were supposed to find the acceleration. So the acceleration is in the x direction, and a sub x is equal to f sub x over m. That is 20 newtons over 40 kilograms. Now look what's happening with units here. So you got kilogram meter per second squared over kilograms, so you can whack the kilograms and you get a half meter per second squared. The force is constant, so the acceleration is also constant. And there you go. Let's look at maybe a more complicated example. This is called the Ketchup Slide. Ketchup is something like is a sauce you would put on a piece of meat or hash browns or something like that. Okay, so in this problem, the acceleration is caused by a frictional force, a different kind of force than what we talked about on the other one. Because in fact, the previous example, we had no friction. So a counter attendant, that's a server in a restaurant, in a diner, shoves a ketchup bottle with a mass of 0.2 kilograms along a smooth, level lunch counter. The box leaves her hand with an initial velocity of 2.8 meters per second, but as it slides, it slows down because of the horizontal friction exerted on it by the countertop. The bottle slides a distance of 1 meter before it comes to rest. What are the magnitude and direction of the friction force acting on it? Okay, so here's a picture. We put some, and pictures are really useful. So we just arbitrarily call this 0, but the server in this diner shoves this along the counter. This was the initial velocity. V sub 0 is 2.8. But then it eventually stops, and it stops 1 meter down the counter. And so you see there's a deceleration. It goes from 2.8 meters per second down to velocity being 0. Now when we analyze the forces then, what is happening? Well, so what happens is that there is a force of friction that's resisting the motion of this sliding down. So that's the force of friction. And then you do have the weight, what's going down on the counter, and that's balanced by the normal force of the counter pushing up on the bottle of ketchup. Okay, so that's what we're going to be studying. Now this is motion in a line, so we need to find the relationship between Vx and Ax. So we use the fact that, and this is one of our equations that we had, and this is the one, by the way, that does not involve time, because no one told you anything about time, so that makes you think this is a good equation to use. So recall this is V sub x whole squared minus V sub 0 in the x direction whole squared is 2a sub x times x minus x0, and that's an equation we had before, and that'll be provided in your grace notes, but you have to know when to use it, and a clue to use it was no one told you about any time. So the initial x component of the velocity V sub 0x was 2.8 meters per second, and the final was V sub x is equal to 0 because it stops. Also, because of our coordinate system, x0 is 0 and x is 1.0 meters. So once A is known, we can use the component form of Newton's second law, this one, to find the magnitude F of the frictional force, because F is the only horizontal component of the frictional force. So the summation of these is going to be minus F. Okay, so let's work to find the acceleration. So we start with this equation, and the only thing we don't know is the acceleration. So we plug in the values. V sub x was 0. That was V final. Minus, this is V initial, squared. This is 2ax, and that's x and x0. So you see we have all those things except for ax. So when we solve that for ax, we get that that is minus 3.9 meters per second squared. So now we can find the net force acting on the bottle. It's minus F, and that is equal to ma. And A came from here. So that is minus F is equal to mass times the acceleration. And we do that calculation, multiply those two numbers. And you note that when we multiply those two numbers, we get kilogram meter per second squared. So that means that actually ends up being newtons, and this is minus 7.8 newtons. Since the frictional force is the only horizontal force acting on the bottle, this gives us the magnitude. And the fact that it acts in the negative x direction was something we already knew from the setup of the problem. Another example here. When the mass of an object is small, this has to do with a TV picture tube. When the mass of an object is small, even modest forces can cause very large accelerations. In a color TV picture tube, an electric field exerts a net force with magnitude. This is 1.6 times 10 to the minus 13 newtons. Now that's not a big number. 10 to the minus 13th is a small newton, but this is acting on an electron which has a very small mass. And here's the mass, and this is 9.11 times 10 to the minus 31 kilograms. That's a real tiny mass. And it asks what's the accelerations? What is the electron's acceleration within that electric field? Okay, so when we draw the picture, we get this. Here's the mass. There's the force. And the only thing we don't know is the acceleration. So we say, well, F is equal to ma, and this is only going in the x direction. So the acceleration in the x direction is the summation of the forces divided by the mass. So we have this. Now everybody realize that we're taking 1.6 times 10 to the minus 13 newtons divided by 9.11 times 10 to the minus 31 kilograms. So when you do these units, that's going to be kilogram meters per second squared. We get kilograms here, so those cancel. And so what we do get when we do the calculation is, and we do have to deal with these exponents, that's 10 to the minus 13, that is 10 to the minus 31, that's 10 to the 17th. So the answer in scientific notation is 1.76 times 10 to the 17th meters per second squared. Kind of a qualitative thing. Again, I'm not going to be giving you these kind of questions. If we're doing this in a classroom, I might do a poll on this just to see if you are feeling good with the concepts. This is about raising a toolbox. Suppose you use a rope to hoist a box of tools vertically with a constant upward acceleration. This is something that sometimes workers will do if somebody is at the top of a chimney doing some caulking of the brick chimney. They might have an assistant put some tools in a box, and they might use a rope to haul it up vertically. How does the magnitude of the tension in the rope compare to the magnitude of the weight of the toolbox as you lift it? Okay, and so here are your three choices. The tension in the rope has a greater magnitude than the weight in the toolbox. It's equal, or it's smaller. Okay, so you should pick an answer, and we'll talk about the solution. Because the toolbox has an acceleration that points upward, Newton's second law tells us that the net force acting on the toolbox must also point upward. Therefore, the magnitude of the force pulling the toolbox upward must be greater than the magnitude of force pulling the toolbox down. That's gravity. That means the correct answer is A. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.